So in the past couple of weeks, we have been introduced to vector fields, conservative vector fields, line integrals over scalar functions, line integrals over vector fields, and most recently, Green's theorem. And Green's theorem was a way for us to evaluate a line integral over some path C. And we could either go about doing it as, actually evaluating the line integral over C like so, or it turned out that if we had this closed region D, we could simply actually just do kind of an area integral, if you will, a double integral. And it was of this kind of weird quantity that hasn't quite fully been explained yet. dq dx minus dp dy. Said you could do one or the other. And so Green's theorem is really nice because we don't have to really parameterize C at all or figure anything out. We just figure out, okay, how do you describe this region? And then you just evaluate whatever that function is and we are done. So Green's theorem ended up being really nice. So this video is going to start to give us an understanding really of where this comes from. And the end goal is to eventually be able to do line integrals in 3D space, and eventually what we call surface integrals, because the next natural intuition is if I can calculate the amount of a function, right, the total value of a function, or let's say the total energy expended by a fly that's kind of following a specific path. It would be really cool if I could do it for a surface as well, something where I'm like, all right, what if I just want the path of a surface? Because before in this class, we've done integrals over entire 3D shapes, right? We've done them over entire 3D shapes or 2D areas, but what if we have a 3D surface? Just like here, we're not calculating the total value of a function over this entire region. We only want to talk about the outline of this shape. And so that's kind of where we're heading in this class and where we will finish our journey in vector calculus. But before we get to all that, we have to define a few things, as is suggested by the title. So we're going to revisit everything that I just wrote down, but for now we are going to start with this first topic. And the first thing that we're going to cover is going to be this idea of curl. Okay, so I think the best thing to do is to kind of give an intuition of what curl is. So in a vector field, by the way, all of these examples that I'm going to give are going to be done in 2D. However, they most naturally occur in 3D, but I will draw them in 2D to kind of build some semblance of intuition for what we're doing. Okay, so in a vector field, okay, we have a whole bunch of vectors pointed in a bunch of different directions, okay, like so. And the idea behind curl is if we imagine this vector field representing if we imagine this vector field representing water or something of that nature, okay, the idea of curl is at a particular point in the vector field, it kind of measures the tendency for the water or the vector field to kind of swirl or rotate, okay? And this is going to prove quite interesting to us because it relates very strongly to Green's theorem. But that's kind of the idea, right? So these tools that we're going to build up today are ways of kind of further breaking down a vector field and analyzing some properties about it, because a vector field could represent the flow of water, the flow of air, things like that, and it's cool to have some sort of vector function that describes a vector field, right? If we had a 3D vector field, we'd have some P, Q, and R components and stuff like that, but it would be really cool to get some more information about it, like say if we were trying to determine, if we were meteorologists trying to determine if a hurricane was going to form, it's a good idea to be able to calculate the curl of, say, the weather gradient or something like that to determine whether or not we're going to start getting swirling, are we going to get tornadoes, are we going to get hurricanes, things of that nature. So the idea here is, can I analyze can I analyze a vector field in such a way that I can determine this thing which we call curl, the amount which something is swirling? And the answer is, of course, because otherwise this section would be pretty boring, the answer is going to be yes. And so here's how we're going to try and think of this formula that I'm going to write down, and then I'm going to write the formula and kind of describe it a little bit. So let's just start with a single vector, okay? A single vector in this vector field kind of looking like so, all right? Now, if this is a 2D vector field, either this vector, the next vector over, if I were to draw a point right here, it's either going to, be pointed this direction, or it's going to point the other direction, right? That there's only two directions that we can go. Basically, this vector can really only experience change going to the left, to the right, or it could experience no change at all, and we're going to ignore that case for a second. We're going to assume that if, we're talking about the flow of air, the flow of water, that either, even though the wind is kind of blowing in this direction right now, that, a little bit of wind overs might be blowing in this direction like so, or it might be blowing in that direction like so, and that we're going to get kind of this change in the wind. Okay, that's going to be our idea here. And so the question is, how do we quantify this mathematically? Well, if you kind of think about it, back in Calculus 3, we had something that measured how much a vector was changing, or how much a function was changing, and those came in the form of partial derivatives. And specifically, we used to talk about this thing called the gradient. And the gradient of some function was basically the act of taking the partial derivatives of that function with respect to x, the partial derivatives of that function with respect to y, and the partial derivatives of that function with respect to z. Okay, and it turns out that this notation could be broken down as something like this, and I'm just going to kind of write it down and kind of see if this makes sense to everyone. Okay, so we're going to do this multiplied by the scalar function f. So what do we have here? We have some scalar function, right? This thing pops out numbers. And this right here is what we call the del operator, or the del vector. Okay, so whenever we had this notation for the gradient, what we were doing was examining, how much each component was changing of this function in a particular direction, and that would give us, say, the direction and the magnitude of greatest increase. That was the whole bit about the gradient. So this vector right here, this is important, this is going to be called the del operator, the del vector. And so where does it come into play? Well, what we're going to do, the formula for curl, okay, the formula for curl looks something like this. It is the del operator cross the vector field f, okay? And so it's important to notice that when you take the cross product of two vectors, right, we have one vector here, we have a vector function here, what are we going to get out? Well, cross product gives us another vector, so the curl is a vector. And the best way to think about it is that if this vector in pink here is my vector f, and the vector in green here is my del vector, right? That's kind of like representative of the direction of change for this vector, okay? It could point to the left, like so. Maybe, maybe it points down here like so, right? Could look something like that. If you've taken a physics class, we have something that we call the right-hand rule. Okay, the right-hand rule, because we don't like lefties. I'm just kidding. But we have the right-hand rule. And the way the right-hand rule works is it says, when you're calculating the cross product, this is something we learned about whether or not the cross product was going to point up or whether the cross product was going to result in a vector pointed down. The idea is that you're going to take your right hand, you're going to put your pointer finger, your index finger, you're going to point it in the direction of the first vector, so the del vector here. Then next, you're going to point the second one, maybe I should have drawn this the other way, but here we go. So you're going to point your second finger in the direction of F, okay? And if you do this, the direction that your thumb ends up pointing in, gives you the normal vector, okay? So for this case, if I point my first finger in this direction and I point my second finger in that direction, my thumb is going to end up pointing straight down. It's going to point down like this, okay? So try it yourself. Point your first finger to the left, point your second finger in the direction of the vector F, and you're going to notice that your thumb points straight down. And the question is, so this right here is representative of del cross F. And now what does this vector represent? Well, this vector, just like any other vector, comes with two things. It comes with magnitude, and direction. And the question is, what does this cross product give us? What does this new little del cross F give us? Well, we talked about curl, and so the idea is, again, if you're taking a physics class and you do that cross product and your thumb ends up pointing down, the way that your wrist would naturally curl in, or the way that your fingers would naturally rotate in, is going to indicate the direction of rotation. And the best way that I can think about this, the best way I can think to show you without being able to do it in person is, let's just imagine that we have a ball, okay? Let's say this ball represents our like just our particle in space. So our ball is indicative of like this space right here. If you calculate del cross F and you get the curl vector, okay, let's say our curl vector were to point out this way like so, okay, this is our curl vector, del cross F. Here's what will happen. Number one, what this tells us is that our ball is going to rotate in this particular direction, okay? It's going to rotate like so. That tells us that our ball is going to rotate counterclockwise, kind of about that particular axis right there, okay? And now what do you think the magnitude represents? Well, the magnitude corresponds to the amount of rotation. The amount of rotation happening in our vector field, okay? Happening in F at that point. All right, so in 3D, it's a little easier to think about. In 2D, it's also kind of simple to think about. So let me erase kind of this drawing here, and let's just imagine. Let's imagine that I still have my vector F, okay, and it's pointing in this direction, and my del vector, the amount of change is kind of like, let's say, let's see, where should I put this? It's happening in this direction. So we put one finger in the direction of our del operator, the other in the direction of F, and in this case, it results like so. Okay, in this del cross F vector kind of pointed down, it's a normal vector. And if this is in 2D, right, what direction are we going to end up rotating? Well, it should kind of make sense that we get some sort of rotation happening, right? Because if we take every vector around this point and we do this and we create the del vector for all of them, okay, then naturally it seems that they're going to rotate about some sort of vertical axis, and these are going to all rotate like so. Okay, so that is what the curl vector is. It's kind of what it represents. It gives us a way to kind of manifest the amount of rotation that is happening in a vector field at any given point, and it manifests itself as a vector. Okay, so let's take a look at this. So for 3D, okay, so in 3D, we would have a vector field F that is equal to something with three components, P, Q, and R. And the del operator would be ddx, ddy, and ddz, like so, okay? Now, if we take a look at what this cross product ends up giving us, del cross f, right? Hopefully by now we know how to do the cross product of two vectors. So we put an I component, a j component, a k component. These are all technically the unit vectors, so little hats. We put the p, the q, and the r, and we put the d, dx. Oh, I'm doing it backwards. It is del cross. It is del cross f, not the other way around. So d dy, d dz, and then we do our p, our q component, and our r component. What is it that we're going to get? What does the curl give us? Well, if we do this process, we're going to get another vector, and this is what we get on the inside. We get dr dy minus dq dz, comma, dp dz minus dr dx, and we're going to get dq dx minus dp dy. Now, let's just remember what this is again. So what this right here is our curl vector. It is the thing that it points in a particular direction, and that direction indicates which way we are going to rotate. It indicates which way we're going to rotate. Okay, we rotate around this vector, and then the length of that vector indicates the amount of rotation we will experience. Now, if you're a very eagle-eyed viewer, you may have noticed something kind of interesting, and that is this component right here. That looks very similar, should look very similar to when we used Green's theorem that said solving a line integral ended up just being this nice dq dx minus dp dy with a dA, and that all we had to do was to solve this to evaluate a line integral. And now that we kind of have a notion of what curl is, I kind of want to deep dive this just a little bit more. And what I want to do is I want you to notice that in 2D, my vector field f does not have a z component. It has a p component, a q component, and the z component is 0, which means that my del operator, I could still put it together, because technically the cross product only exists in 3D. But when I do the del cross f operation to get my vector, I get 0, 0, and I'm only going to get this last component, which basically says, right, that this del vector points in what direction? Well, it does not point in the x direction. It does not point in the y direction. It only points in the z direction, which should make complete sense, because if all we have is the x and the y axis, we have a bunch of vectors that are pointed on this, from this vector field, and we're wondering what direction are they going to spin. Well, then the only possibility would be to get a curl vector, our del cross f, pointed in the z direction, right? And that's going to indicate that, oh, this is going to curl, that this vector is we're going to swirl kind of around this vector like so. So it makes sense that the amount of curl that we experience in a 2D vector field basically only has a z component. This vector only has a z component. So the more interesting question is, how does this relate to Green's theorem? Okay, so Green's theorem, right? I said it at the beginning of this video, but Green's theorem basically is a way of saying if we happen to have a closed line integral, okay? So a line integral that is closed over some path c, right? This is the path c. And we're trying to evaluate this vector field over this particular path, right? We want to calculate the total amount of work or the total amount of energy that the fly is giving off as it's zooming around on this path in 2 dimensions. Here's x, and here's why, okay? The Green's theorem, what Green's theorem said is that we only have to do this, and we saw that this was dq dx minus dp dy, and that all we had to do was this area integral. But now that we understand what curl is, this right here is basically the curl. It is the curl vector. It is the k component, the z component of the curl of f. So maybe I'll say this is the curl of f, but just the k hat component. Now, again, the whole point is, why does this even work? Because I gave you Green's theorem and was like, here is a formula, go ahead and use it. So let's talk about why this works. Okay, the idea is that over this entire domain, okay, over everything inside here, I'm gonna highlight it. I'm gonna take the time to actually highlight it. So over this entire domain D, there are infinitely many points on the inside. Okay, infinitely many points, and at each of those points, there is some bit of curl, and I'm going to indicate the curl by simply just drawing like some arrows around it like this, okay? There is curl. Now, whether it is clockwise curl or counterclockwise, so counterclockwise, the way I've drawn it, would be positive curl, and negative curl would be pointed the other direction, okay? If you look at the point next to it, okay, in theory, provided that this vector field doesn't have any weird discontinuities or any sharp, non-smooth components, then the curl immediately next to this point should exhibit, relatively speaking, the same behavior. Actually, let me draw this in a different color. It should exhibit, almost the same behavior. And so we're just going to draw that by putting these arrows in like so. And the point next to that should also exhibit pretty similar behavior in terms of the curl, okay, on kind of a microscopic level. And if we do this for every single point, okay, if we do this for every single point, we calculate the curl at every single point, and we zoom in, you're going to notice something, okay? So this double integral right here basically is adding up, okay? It's adding up the total curl over this 2D region given by D. Now, how the heck does that equal a line integral, right? This is not super clear yet. Well, check it out. Notice what's happening at all of these points is that the curl kind of cancels itself out in every single place that is on the inside of D, right? So in other words, that the curl, maybe I'll do a highlighter. Okay, the curl right here, the curl right here, the curl right here. If I were to, pick another point here and demonstrate the curl here, okay, then we would get back to getting cancellation right here. The idea is that the curl kind of equals 0. It equals 0 at all of these points. That the amount of curl that we get kind of cancels out. And the only place where it doesn't cancel out, the only place where the curl does not cancel out is right here at the edges. Okay, if we get close enough, if I zoom in and I put a point right here and I'm doing a curl calculation and I get something here and something here and something here and something here, the idea is that this part of the curl right here is going to cancel out with whatever's next to it. And this part of the curl is going to cancel out. And this part of the curl is going to cancel out with whatever point would be to the next of it, and to the next of it, and to the next of it. And the only sides that are not going to cancel out are going to be the part of the curl that is essentially directly on this boundary, because there are no points to the right of it or above it or below it that are going to cancel out that little bit of the curl. And so in mathematics, this might seem like a little bit of a stretch, but basically what this says is that when we're doing, using Green's theorem, and we're calculating the total curl of F over this region D, dA, when we're doing this, that basically this is the exact same thing as what we would get if we had gone about calculating the closed line integral of F in the first place, right? That basically, we're basically calculating the amount of F going in the direction, right? At every single point on the boundary, we're gonna get the amount of F going in the direction of the curve all the way along for every single point, right? We take every single point, calculate the curl, and the only pieces that are going to survive are these boundary pieces, which, if we remember how I told you all to think about calculating a line integral as the amount of the vector field F going in the direction of our curve, then these two are exactly the same, okay? So this is what curl is, okay? It is this cross product, okay? It's this funky little concept. It's this cross product, and it gives us an orthogonal vector, and that orthogonal vector represents it gives us the direction which we curl, which we said, again, if it points up here in space, then it's going to kind of curl kind of in a clockwise direction there. If it were to point, say, like down in space, then it's going to go in a counterclockwise direction, again, using the right-hand rule. And that's something that's very difficult for me to show you, on a drawing. I wish I could show you in person, but you can just Google right-hand rule and it will very quickly come up. Okay, so that's curl. The curl is a concept. It's a vector. It represents the amount of rotation that the vector field experiences at a particular point in the vector field. Okay, it results in a vector. So, for example, let's do an example calculation. Given the vector field, we can keep it, well, I guess we can make it 3D. Let's do xz, comma, x squared y, comma, yz. Let's say I give you this vector field and I ask you to calculate I want to know what is the curl of F. Okay, the way that we're going to do this is we're going to do the del operator cross our vector field F, and we set this up doing our I, our j, our k. We put in our little del operator, d dx, d dy, dz, and you can use the formula that I gave you above as well, but I'm just kind of going to show you, this is exactly what it is. Okay, we're determining how much rotation we're getting at any single point. And if we go about doing this, right, so if we do the first one, we're going to get so we cross out this part and we're going to get the partial of yz with respect to y. So I'm going to kind of do some of this, well, I guess I can try not to do most of it in my head, but we cross out this part. What are we going to get? So the partial of yz with respect to y is just going to be z, and then we subtract what we get when we do the partial of x squared y with respect to z, and that's just going to be 0. So it looks like our first component here is just z. Cool. Let's do our second one. So our second one, we cross out the middle, and we do, all right, so we're going to do the partial of yz with respect to x, and that's 0. And then we're going to subtract what we get when we do the partial of z with respect, or the partial of xz with respect to z. And we're taking with respect to z, so we're just going to get x. So that's going to leave us a minus x for this middle component, minus x. And then what are we going to get for the last one? Let's find out. So if we do the last one, we cross out this one, and we're going to get, all right, so the derivative of x squared y with respect to x is going to be a 2xy. And then we are going to do the derivative, so subtract what we get when we take the derivative of xz with respect to y, but that's just 0. So it looks like we just get this. So this right here, this vector right here is the curl, this is the curl of f. at any particular point, okay? And so this means that if you were to say, you know, at the point 1, 2, 3, what is the curl of f? We could calculate it. We're going to get some vector, and in this case, we're going to get the vector 3, -1, and it looks like 4. And so this vector right here basically says that in 3D space, we're going to have the point 1, 2, 3. Maybe that's right there. And we can put in this curl vector, which is 3, -1, 4. So, you know, maybe it points this way, and this is the vector 3, -1, 4. And that kind of gives us some intuition that we're going to experience rotation in this vector field kind of in that direction, okay? And so that's how calculating a curl vector goes. Fabulous. So actually, I'm going to stop this video here, and I'll split this video up. I was originally just going to do this all in one go, but I'm just going to make another video that has divergence and flux in it, so as to not overwhelm you all completely. So try to watch this video. There's a really good intuition of curl. If you go to Khan Academy, there's a really good intuition of curl. Just type in 2D curl intuition. Right, 2D curl intuition into Khan Academy, and watch that video specifically at like 52 seconds. The 52-second mark is pretty good. So check that out, and then hop into the next video where we start talking about divergence.